Okay, so one of the a special series. So we have geometric series, we have that arithmetic series, but a special series that's kind of cool is something called a p-series. Now, a p-series will always be of the format sum n equals 1 to infinity, because we're talking about infinite series, of 1 over n to some power. Now, what I mean by that is we're talking about 1 over 1 to that power plus 1 over 2 to that power plus 1 over 3 to that power, and so on and so forth, all the way up to 1 over n to some power, and that'll obviously keep going infinitely on. Okay, so we call that when we're actually, we have an exponent, but we're raising whatever's in the series to that exponent, we call that a p-series. Now, p is a positive constant, so we're only talking about positive exponents. Now, there is a special p-series, and you need to put like mega, 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 mega stars. If p is 1, we call it the harmonic series. So what I mean by that is if p equals 1, then this is the sum from n equals 1 to infinity of 1 over n. Now this is a super special series because we're talking about p is 1, so this means this is to the first power. So that means that our first term is 1, our second term is 1/2, our third term is 1/3, our fourth term is 1/4, and so on and so forth. Okay, so that's a very, very, very special p-series. Now, I want to actually use the integral test to come up with a new test. So let's say the integral test is the only thing in our arsenal, and I'm going to use this integral test to figure out what values of my exponent would cause a p-series to converge. And this is going to lead us to develop our next test. Okay, so let's start with p equals 1, which is our harmonic series. Now that is a very special series. Okay, so our harmonic series, which we've already listed out, we know is 1 plus 1/2 plus 1/3 plus 1/4. Like, I can tell that this is positive and it's clearly decreasing, but I don't know whether this converges or diverges. So we're going to use our integral test. Integral test says we're going to say sigma n equals 1 to infinity of 1 over n, and instead of a series, we're going to now write an integral. We're going to start at 1, go to infinity, 1 over n, dn. Now, because that's not something that I can do, I have to write a limit. So I'm going to say limit, not as n approaches, we need another variable. Not n, how about t approaches infinity, integral from 1 to t of 1 over n dn. Now, we know that I can take the antiderivative of 1 over n and get natural log of n, and evaluating that from 1 to t. So I have the limit as t approaches infinity of the natural log of t minus the natural log of 1. If I sub in infinity, I have the natural log of infinity minus the natural log of 1. This is 0, and this is going to diverge. So I can respond and say that the p-series will diverge by the integral test if p equals 1. So far, p equals 1 does not converge. Okay, so let's see if we can come up with a rule. What about if p equals 2? Okay, so if p equals 2, what does that look like? Well, that's saying 1 over 1 squared, which is just 1. 1 over 2 squared, so 4. 1 over 3 squared, which is 9. 1 over 4 squared, which is 16. And keep in mind that all of these series are going to keep going forever and forever and forever. Okay? So when I say p equals 2, I'm talking about the instance where we're saying the sum from n equals 1 to infinity of 1 over n squared. Okay? So using our integral test again, let's figure out what this thing is doing. Integral from 1 to infinity of 1 over n squared dn. And I have to rewrite that as the limit as t approaches infinity, integral from 1 to t. I'm going to rewrite this as n to the negative 2 dn because we're going to use power rule. And I get the limit as t approaches infinity of n to the negative 1 over negative 1 evaluated from 1 to t. So the limit as t approaches infinity, negative 1 over t minus negative 1 over 1. So let's direct sub. I direct sub, I get negative 1 over infinity, and that's going to become plus 1. So my negative 1 over infinity, that's going to go to 0, and I get a value of 1. So what does that mean? That means that if my integral is converging, then this series is going to also converge by the integral test. Okay, so p equals 2 works. So that's kind of unusual. What about if p is a fractional value? Okay, so what if p was a fractional value? So what would that look like? Well, that means the exponent is 1/2. So my series is going to be 1 over the square root of 1, 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, which would be 2, 1 over the square root of 5, and so on and so forth. Okay, so what does my series look like? My series is n equals 1 to infinity of 1 over n to the 1/2 power. And we're going to rewrite this as an integral to do our integral test. Now, the integral test is really not practical for this because we're going to come up with a rule. But we're using the integral test to show you that it's still valid, and this integral test will tell me kind of what I want to know. So I've got 1 over n to the 1/2 power dn, and we're going to rewrite that as the limit as t approaches infinity, integral 1 to t n to the negative 1/2 power dn. If I take the antiderivative of that, I've got the limit as t approaches infinity of n to the positive 1/2. Divide by 1/2 makes that 2, and we're evaluating this from 1 to t. So I'm going to get limit as t approaches infinity, 2 square roots of t minus 2 square root of 1, which is just 2. So subbing in, I get 2 square root of infinity minus 2, which is going to be infinity minus 2 or infinity. So therefore, this is going to diverge by the integral test. So this one diverged. So can we come up with a rule? If p equals 1 diverged and p equals 1/2 diverged, but p equals 2 converged, maybe I can come up with a rule. So that rule says if you have a p series where I'm raising this to some power every single time, things you need to know. Number 1, it's going to converge if p is greater than 1. It's going to diverge if the p, the exponent, is between 0 and 1. If p equals 1, it will diverge, and that is your harmonic series. Okay, so how will this work in action? Here are two p-series. Okay, how do I know that they are a p-series? Well, I know that they are a p-series because this is the sum from n equals 1 to infinity of 1 over n to the 1/3 power. I see a power on a variable. That tells me that this is a p-series. It is a p-series with p equal to 1/3, which is less than 1. Therefore, this diverges by the p-series test. And I don't have to integral test it anymore because the p-series test takes care of that for me. I look at the next one. I'm like, hey, that's a p-series too. It's also a p-series with p equal to 5/4. Because that is bigger than 1, this is going to converge by the p-series test. And I no longer have to do the integral test. So this is kind of nice. Something I will caution you about is on your homework, I might throw something like this at you. You might see something like the sum of 2 over n to the 3rd power. That is still a p-series because I can take that 2, because everything would have a 2, and put the 2 on the outside. So you can still treat that like it's a p-series. You're going to see that hit you in the face on your homework. Good luck, and hope this was nice and short.